Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Yeah, welcome everyone to this webinar series from molecules to models. And today it's my pleasure to introduce you to Arthur Gritton. He is a professor at the Gatsby Computational Neuroscience Unit and director of the Center for Computational Statistics and Machine Learning at the University College London, UCL, as well as a research scientist at Google DeepMind. And he's also an Alice Fellow on the Alice Unit Director London. He holds the degrees in physics and systems engineering from the Australian National University and a PhD from the University of Cambridge and conducted with Microsoft Research. And other previous positions include research roles at the Max Planck Institute for Biological Cybernetics and the Carnegie Mellon University. And Arthur's current research focus on the causal inference, representation learning, generative models, and non-parametric hypothesis testing. And Arthur serves as an editor and senior area chair for the leading journals and conferences such as GCML, IEEE, NeurIPS, ICML, and ISTATS. So Arthur, the floor is yours.
Right, thank you for the invitation. I'm just going to share my slides. So hopefully this is now visible. Great. Yeah, so, oops, there we go. I need to open. Yeah, so the talk is basically a talk called Learn How to Do From What You See, Causal Effect Estimation. I want to emphasize that I like to get questions during the talk, so please feel free to message Conrad, who will then direct questions to me at any point during the talk if anything's not clear or if you'd like to sort of explore some of the themes in more detail. Great. So I'm going to begin with a simple sort of synthetic example, which is a medical treatment scenario. So imagine that I'm an administrator in a hospital and I'm observing the effect of treatments on an outcome. And for the illness that I'm considering, there are one of two treatments. So one treatment is to provide pills to the individuals, and the other treatment is to provide surgery. So the treatment I'm going to write as a node A here. And then this node A is going to have some influence on the outcome. And so the treatment is going to result in the patient being cured. So this is Y being positive. Muted. Yeah, sorry. Yeah, so either the patient is cured or the patient is not cured. All right. And in this observed setting, the chance of being cured, given that pills were assigned, is 0.85, and the chance of being cured, given that surgery was assigned, was 0.72. So now, as an administrator, I might conclude, well, pills are cheaper, pills work better, so from now on, everybody gets pills. So once I make this decision, I'm performing an intervention on the system. So I'm stopping observing and I'm intervening. So pills are more effective, pills are cheaper. The intervention that I've placed here, I've then drawn as a node with a double boundary to denote that I'm actually intervening on the system now rather than just observing it. And following this intervention, I see the following results, that the chance of being cured, given my intervention that everyone gets pills from now on, is 0.64. chance of being cured under intervention surgery is 0.75. These numbers are quite different to the numbers here. So a question might be, well, what error have I made when I made this conclusion? I should also emphasize, by the way, that the result of an intervention is the intervention is written as a superscript to denote what my intervention was. So Y superscript A indicates that I've basically intervened with pills on my population of patients. So let's now look at the error that I've made. What I've failed to account for is the context in which the doctors have historically made their decision. So when the doctors were previously treating the patients, they were actually following a procedure. And the procedure that they were following depends on the severity of the underlying disease. So the severity I'm writing as a note here, which is X. The disease can take one of two forms. So it can be like a mild form or a severe form. And historically what the doctors have done, they've looked at the severity of the disease. And then they've prescribed pills, more likely when it's a mild form. They've prescribed surgery, more likely when it's a severe form. And then based on the severity and the prescribed treatment, we get the outcome that the patient is cured or not. And so this leads to our numbers here. So how do we obtain these numbers? Well, we obtain the numbers from the formula up here. So let's break it down, right? Here's the chance being cured, given the treatment and given the severity. But now we're saying, look, what happens when we know that the patient was prescribed pills? Well, if we know that the patient was prescribed pills, then it's more likely that it was a mild form of the disease and less likely it's a severe form. So this gives more weight to the mild form, less weight to the severe form. Conversely, if we were prescribing surgery, if this was surgery, then we'd give more weight to the severe form and less weight to the mild form. And so this equation here describes the system that was in place when the doctors were assessing the patients, deciding on a treatment, and then based on the assessed severity and the treatment, we have the outcome. Now, what did we do when we intervened? Well, when we intervened, we broke the link between severity and treatment, right? The intervention here is everybody gets pills. So regardless of severity of disease, we are going to assign pills to everybody. Now, this gives us the result down below, and the equation governing that is given here. What you'll notice is you've again got the chance of being cured, given the treatment and given the severity, but now we just give everyone the same treatment. So we average over mild and severe cases, but we don't have this sort of like unequal weighting of severity conditioned on treatment, because now everybody is getting the same treatment. Okay? So this is known as Simpson's paradox, even though it's not a paradox, it's common sense. But this gives a sense of the pitfalls of intervening based on what you observe, right? If I had just observed, pills having a better cure rate and I had intervened accordingly, I would have not accounted for the fact that historically context was being used to decide on the treatment pills. And so this is the mistake that I made. So this is sort of to clarify the distinction between observation and intervention. So now let's proceed. So what kinds of questions are we going to answer in this talk? One question is, can we obtain the average causal effect, which is to say the average effect of an intervention, based on historical data? So if we've observed this hospital setting for a long time, can we actually predict these effects of making an intervention? Okay, so this is fine, but it's also, as I've expressed it, not a very interesting question, right? Because you're saying, well, everybody gets a given treatment. Like, this is not how a hospital works. A more interesting question might be something like, conditioned on looking at a population of patients' high blood pressure, what would be the effect of giving them blood pressure medication? So let's say that V is high blood pressure. All right, A is blood pressure medication, and then Y is my outcome. But I've also got this X, and the X here is remaining patient demographics aside from the blood pressure. And this is linked to V, right? So let's say I have high blood pressure. Well, it's more likely that my age is from 40 to 60, let's say. And it's not likely my age is from 10 to 15. So knowing that I have high blood pressure tells me something about age. Now, I'm drawing this arrow as a dashed arrow with two points on it to indicate that I'm taking no position about the causal influence of V and X, right? It might be X causes V, V causes X, a hidden common cause. We don't know, we don't care. We just know that there is some interaction between the variable we're conditioning on, in this case, high blood pressure, and the remaining patient demographics. And then, based on, the blood pressure, based on the remaining demographics, based on the treatment, we're going to get our outcome. And so then we can make a statement like, conditioned on the patients having high blood pressure, what would be the effect of intervening and giving blood pressure medication, let's say. Okay, so this is one of the questions we'll address, and it is a more interesting question than just saying, on average, what is going to happen when I give everyone a particular medication. Now, one further point we're going to address is we've determined how important it is to consider context when we're looking at the effect of an intervention on an outcome, right? Because we need to take this average of our outcome, given our treatment and given our context, and average it over these demographic variables. So the next question might be, what happens if I don't get to see this, right? If this is invisible, is there anything I can do? And the question will be, well, how much extra information do I need in order to be able to do something in this circumstance where I'm not able to observe the context relevant to the effect of my treatment? So it isn't completely hopeless, but one has to be very careful. So this leads us now to the outline of the talk. So I'm going to talk about causal effect estimation. I'm first of all going to talk about an average causal effect, an average treatment effect, which is sort of saying, look, on average over my population, what would happen if I made a particular intervention? And can I predict this given my observations of what went on in our hospital prior to my making that intervention? Once we've done that, and we're going to develop some tools in order to do that, we're going to get the conditional average treatment effect. So this is a more interesting case, of the patients with high blood pressure, what would happen if I gave them blood pressure medication? Then we're going to move on to address the question of hidden covariates. So what happens when we're trying to make predictions where the context that we need in order to validate these predictions is hidden to us? I'll mainly focus on a technique called instrumental variable regression. I will also perhaps briefly touch on a more recent approach called proxy variables. Now, one thing I really want to emphasize, and what's sort of new and novel in this talk, is that in the settings that we consider, we're concerned with cases where treatment covariates and so on are very high dimensional. So in many classical studies, treatments are very simple. It's like you give a pill or you don't. But maybe in the cases we consider, the treatment is a radiotherapy regime or the output of an LLM or something which is very high dimensional, very complex. So a treatment isn't just a case of doing something or not doing something. It's something with a lot more structure and meaning to it. Our covariates, of course, are also very high dimensional. It's like all of our patient demographics. In order to treat these high dimensional complex cases, we're going to have to decide on some features that encode the relevant information of that treatment, those covariates. And we're going to use two different techniques for that. We're going to use kernel techniques or adaptive neural net techniques. Okay. So this is the outline. As I say, any questions at any point, please let me know. Great. All right. So we're going to keep this talk simple. This talk is only going to have one model, like one basically like regression that we need to learn, and there's only one algorithm to learn it. So this is quite convenient. The model assumption that we make is that every function that we learn in this talk is going to be a linear sum of features. Okay, this is a very simple thing to ask. But when we say a linear sum of features, we actually have a choice. We can make these features neural net features. Okay, so that means a dictionary of learned features that we learned from our data. And I've given some citations here. Or we can have fixed dictionaries, but they can be infinitely long. So rather than having finitely many neural net features, we have infinite dictionaries of fixed features. Okay, now infinite dictionaries are very hard to fit in computer memory, but we have a trick that we can apply, which is that if our algorithm only uses dot products between these infinite feature dictionaries, so if our algorithm can be expressed solely in terms of dot products of, let's say, an infinite dictionary of features of xi, a training point, and x, a point at which I'm making a prediction, then in the cases we're going to consider, this dot product can be expressed in closed form. So even though I've got infinitely many features, I have a dot product in closed form. And so as long as I can express my solutions in terms of these dot products, then I can still deal with these infinite feature dictionaries. So basically, I'm using these infinite feature dictionaries, but I'm using them implicitly via their dot products with other features. All right. So these are, I'm making this modeling assumption, but I've got two different choices of how I might express my features. So let's first of all address the case of neural net features. All right. So I said there's only one model, linear combination of features. I'm going to fit it using just one approach, which is called ridge regression. So that's the only algorithm you need to know for this whole talk. I'm going to fit ridge regression. Yeah. So what is ridge regression? Well, there's two components to it. One is that here is the function I'm learning, linear combination of neural net features. I'm going to use that to predict my y, right? My outcome, the patient being cured or not. I'm going to use here a squared loss. So this is the loss I'm going to use for my regression. And in addition, I'm going to add a term here, which is basically the sum of the squared values of these gamma features. So these basically are features that combine my neural nets. So having this sum of squared things stops any of these features from getting too large and sort of dominating my calculations. So here is in a figure what this looks like. I've got my inputs. I compute neural net features of these inputs. Then I basically take a weighting of these neural net features, 1, 2, 3, and this gives me my outcome. And I basically choose these gammas to minimize this loss. All right, so there's two things I need to learn here. First of all, there's these gamma weights, and second, there's all of the remaining neural net parameters. So the gamma weights, as it happens, I can compute in closed form. These gamma weights are basically the cross covariance between my neural net features and my y's, multiplied by the inverse covariance of my neural net features with themselves, plus a lambda here from this term here. Okay, so I have these gammas in closed form. I don't have to do any sort of optimization to learn them. I then plug them in, and then I backprop through to get the remaining neural net parameters. Okay, so I'm basically separating out these gammas, these sort of final layer parameters, from all the rest of my neural net features. Those of you familiar with neural nets might be a little surprised by that, and then you might think, why not just treat gamma like everything else? I'm going to leave that a mystery for now, but I'm going to come back to that question shortly. For more detail, though, on this, please see the paper that I've cited at the bottom of the slides, where this is discussed in greater detail. Okay, so linear combination of neural net features. I have the weights of this linear combination in closed form. I then substitute those in. I do backpropagation. I get the remaining neural net parameters. And now I've learned my function. Okay, so every model in this talk is going to be fit with this loss, and it's going to be, using this formulation. Now, what I've just described to you is well and good if I've got finite dictionaries of features, but what if we've got infinite dictionaries of features and I'm doing kernel ridge regression? An infinity by infinity covariance matrix is not very practical, right? So what might these infinite feature dictionaries look like? Well, I've got an infinite feature dictionary, but as I've said earlier, as long as the solution to my regression problem can be expressed in terms of dot products between those features, then I'm okay. Just to give you an illustration of what this looks like, if my kernel function takes this form, an exponentiated quadratic, then you can think of this dictionary of infinitely many features as being features that are getting more and more wiggly. Like as I go down my dictionary, my features are less and less smooth, but the amplitude's getting smaller and smaller. So I've got a function of infinitely many features, but I'm prioritizing smooth functions over rough functions. So I'm using more smooth features or giving greater weight to smooth features than I am to rough features. Now, fortunately for me, this problem here can be solved in this infinite feature dictionary setting entirely in terms of dot products between my features. Okay, so in particular, here is the solution. My prediction, my estimate of my y at x, is a sum of my training y's with weights beta. These weights beta are given by this expression here. The expression has in it a matrix K of dot products between features of my training points that I saw in training, and then this vector here of dot products between my features of my training points and my x. So notice here, at no point do I need to explicitly write down my infinite feature dictionaries. All of the solution is expressed purely in terms of dot products. So, these are the two mechanisms that we're going to use for the solution. Just to sort of clarify when I would use which, these sort of infinite dictionaries of smooth features are very efficient when I have small amounts of data, like in econometrics or settings like that, where I just need like a good set of smooth features to solve a problem, which is very data scarce. Neural net features are better if I've got, let's say, very structured information like images or text, and I've got a lot of data, which is to say enough data to train those features. So broadly speaking, I would use neural net features when I've got lots of data, very complicated features. I would use kernel when I've got not so much data and I want just a generically smooth function. Any questions before I go on? Okay, great. So now I've basically set out the ways that I'm going to solve my regression problem. I'm now going to estimate causal effects. So we can do it with two approaches. As I've said, we can do it using a kernels approach. We can use a neural net approach. We're going to basically explore both of these in this talk. I will emphasize that the code is downloadable for these methods, so please use them. The kernel method was done by Rahul and Liuan in this paper here, and the neural net version was done by Liuan in that paper. So I'm going to focus at first on the kernels setting because it's a little bit simpler. Right. So this is what we're after, right? From observed data, we want basically my average causal effect, which is to say my chance of being cured, given treatment, given covariates, averaged over my population of covariates. Now, I need to make some rules before I go on, and my rules are in purple here. So the first rule is called the stable unit treatment value assumption. That's the no interference assumption. What that asserts is that the pill that I take does not cure the person next to me. It's only going to have an effect on me. So the treatments only affect the individual. This is true, I think, in medicine, but one has to be careful because in let's say other domains like advertising, it may be that people influence each other, so you can get spillover effects. Conditional exchangeability is my second rule. So what I'm assuming is that there's no hidden U up here, which I'm not accounting for, which is influencing A and Y, right? I'm ruling that out for the moment. We'll come back to hidden U's later, but for now I'm ruling that out. Final condition is called overlap. So overlap means that I don't draw conclusions about things I've never seen. Let's imagine that I never gave pills to someone with a severe form of the disease. What would happen if I gave them pills? Well, I don't know. I never did it, right? So I need to have at least seen instances of the things that I'm drawing conclusions about in order to basically make those conclusions meaningful. So these are my rules. Let's now consider the setting which we're going to explore for this treatment effect estimation. This is a US Job Corps dataset. So this is a training program that was run in the US for disadvantaged youths. In this instance, they spend a certain amount of time in the course. And then following the amount of time they spend in the course, they have a lower or higher chance of being employed at the end of the course. The X are all of the demographic information that we know about the individuals taking the course. So their age, education, marital status, and so on. And so what we now want to do on the basis of the observations of this program is to determine the effect of intervening. So of basically saying, if the people enrolled in this program spent a certain number of hours, then what would be the effect on average on their employment? Okay, so let's now do that using the ridge regression technique that we've described. First of all, we notice that our outcome is a function of two variables, right? When I introduced ridge regression, it was a function of one variable. At this point, it's now a function of two variables. It's a function of the treatment and of the covariates. And the question now becomes, how do we assign a reasonable feature of a treatment covariate pair? Let's say that we have a very good feature representation of our treatment, however we've learned it, basically by a neural net, by a kernel method, however we've chosen to do so. And we've got a very good feature representation also of our demographic information. The way that we'll construct a feature representation of the pair AX is by taking a big long vector of products of pairs of features of A and of X, okay? So that's a dx by dA vector, a very long vector of products of pairs of features. Then this is our feature representation, and as before, we take a weighted sum of these features in order to make our predictions. So just to emphasize, the argument of the feature denotes which feature I'm talking about. This is to avoid like lots of cumbersome subscripts. Right. So this is a design choice. In the end, it's not too damaging a design choice. So in the kernel land, this allows me, with sufficiently rich features of a and x, to represent all continuous functions of a and of x. So it's actually a very rich representation. So we're not losing too much by making this modeling assumption. But what we're going to see later on is that, in fact, it's a very useful one. And it's going to be core to the algorithms that we're going to describe. So it's a necessary assumption, but it's not too damaging an assumption. All right. Given that we have this feature representation, we need to express our solution. We're doing the kernel's setting, so we're going to give a kernel solution. It so happens that the solution is, again, a weighted sum of the y's that we observe in training, where the weights are given by this expression here. The only difference with respect to the expression we have earlier is that we have an entry-wise product of the kernel matrix on A, so the dot products of features of the training A's, and the kernel matrix on X, so the dot product of the features of the training X's. Okay, so we've got this entry-wise product of matrices, but apart from that, the solution looks as it did earlier. So using this feature dictionary has a very simple solution when you put it in kernel form. Now, we have the regression function. We've determined the solution of this regression function from training data. Now we need to get our average causal effect. So we take this y given a and x, and we average it over x, right? Because that is the average causal effect. We're just taking the average over our population. We're going to now expand this out. Now, at this point, we're actually done. We don't need to take any further steps. But because of this featureization that we've chosen, and specifically because of that, we are able to take the expectation inside here and express the solution equivalently as the dot product of my linear final layer, my features of A, and the expected features of X. So the mean of these features of X. So we basically take this big vector of average features, then we take the pairwise products of those with the features of A, and then we take the linear final layer. So we did that here, but we didn't need to. I'm just showing you this trick because we're going to be using it shortly in a setting where we do need to use it. Great. Okay. So here is our solution. This is, our expression of y given x and a, and now we just average this over the population of x's, and this gives us our average causal effect. So let's see what this looks like. So here is the number of hours that the individual spend in class. Here is the percent employment. And what you can see is a sort of, diminishing returns effect, where initially, as the individuals spend more time in class, the percentage employment rises, but then after a point, it starts to fall again. And so this is the finding that we have from this data. We're comparing here against an alternative approach to this continuous treatment. We believe that the generically smooth kernel features that we used give a more realistic plot in this circumstance, which is a plot that we have here in blue. This is one of the scenarios where the kernel methods are indicated because there's not much data, and a generically smooth function of that data is probably a good approach. Great. So this is our average causal effect. Again, any questions at this point? Great. So that's the average causal effect. Now let's do the more interesting setting, the setting that's actually more meaningful in a scientific setting, which is the conditional average causal effect. Now, remember the setting that we thought of. If we're going back to the medical setting, V is blood pressure medication. V is blood pressure, A is blood pressure medication, Y is the chance of being cured, and then X is everything else that we know about people with high blood pressure, right? Which is, maybe the obesity or the age or any other sort of information that might be demographic and pertinent. All right. And what we're after here is basically the following expression here, which is to say, what is the effect of an intervention on A, which is to say, what is the effect of applying blood pressure medication to the population of individuals with high blood pressure, which is the interesting question to ask, right? But knowing they have high blood pressure tells us other relevant factors. These factors might have decided historically the treatment that the individuals got, and these factors also might be relevant to the chance of being cured, right? If you've got diabetes, maybe your chance of cure is lower. At this point, y is a function of three inputs, right? A, x, and v. So it's, my chance of being cured is a function of whether my blood pressure is high, it's a function of my remaining demographic information, and it's a function of the medicine that I've been given. All right? So let's now basically express this as a linear combination. In this case, I've got a big long vector of products of triples of features rather than of pairs of features, but it's the same principle as before. Here is now my function, right? And now I have a rather interesting puzzle, right? So I've got features of v given v, and v given v is just v, right? But now I've got my remaining demographic information given v. And the distribution of this demographic information given v is a very complicated object. So let's imagine I'm trying to simulate by a diffusion model or by some other sampling procedure my entire population of people with high blood pressure. Like, what is their age? What is their, obesity? What are the comorbidities, et cetera, et cetera. That's a very, very difficult problem. So learning, let's say, to sample from this population of individuals, given that they have high blood pressure, this seems a harder problem than the problem we want to solve. But it isn't a problem we need to solve. Why is that? Well, we're going to use the trick that I introduced a couple of slides ago, which is because we've chosen this form, we are able to take this conditional expectation inside here and then basically have a conditional vector of feature means appearing along with my features of A and of V. Okay, and learning the means of these features of x given v is a much easier problem than trying to simulate all of x given v. So I mentioned earlier that I would explain why it is that I chose this sort of linear final layer formulation. Now I'm explaining it. I've chosen that in order that I can take this expectation inside, in order that I can solve the easy problem here, which I would not be able to do had I not chosen this parameterization. So now the mystery has been resolved. All right, so let's now continue and solve this problem. What I need here is a conditional mean of my features of x, my age, my obesity levels, etc., given v, given the high blood pressure. How do I do that? Well, there's only one algorithm in this talk, so it's pretty easy. I'm going to do it by ridge regression. Okay, so conceptually, what am I trying to do? I have some good features of v, and I'm trying to learn the mean features of x given v, right? The average of my x features given v. How do I do that? Well, here is my v, and I'm going to say, for the sake of argument, that v has three dimensions here. I'm going to pass them through, a neural net or whatever mapping I choose, and then I'm going to get features of that v, right? And in this instance, I'm going to assume that my features are two-dimensional. Now, I want to use those features of v to learn an expression for the expectation of x given v. And the way that I'm going to do that is I'm going to multiply these features of v by a matrix f. This matrix f is going to have dimension dv by dx, and this is going to give me my vector of expected features of x given v. Okay, so that is going to learn this vector of expected features. So my goal in learning this conditional mean is to learn this matrix. How do I do it? Well, there's only one loss in this talk. This loss is the ridge regression loss. So I've got my features of v. I have now a matrix, and this matrix maps from my features of v to my features of x. And then here I've got this trace of f transpose f. So this is effectively the sum of the squared entries of f. What that amounts to doing is sort of separately regressing, effectively, from my features to each of these outcomes. So I've sort of regressed to this one, and then to this one, and then to this one independently. Okay, so this is what I've got here, and I'm going to solve this with ridge regression. In the event of using neural nets, I have a closed form expression for f, as I showed at the earlier point in the talk. And then I backprop through to solve for the remaining neural net features of v. So this is how I train this neural net that I showed in this diagram here. What about kernels, right? If I'm doing this with kernels, then this is an infinite feature dictionary. And this is also an infinite feature dictionary. So this is an infinity by infinity matrix, right? This seems like a very, like, impractically hard problem to solve. Turns out that it's not. Okay? It turns out that the solution that you get looks exactly the same as the solution you got when you were mapping to a scalar y. So here we're mapping to these features of x, but the solution to the conditional feature mean of x given v is again a linear combination, like a weighted sum of the features of my training x, where these weights are given by the exact same expression that we had when we were mapping to a scalar y. The intuition is that we're effectively doing independent regressions for each of the coordinates of my x. So we're sort of like saying each of my features of x, I'm just doing a separate independent regression to each of those values. And that regression is going to have the following weights. Okay, so once again, the only algorithm in this talk is ridge regression. We've done ridge regression. We've learned this f. This f has then enabled us to compute the conditional mean of my features of x given v. All right, so now we have that. We can compute our average causal effect. Okay, so conditioned on high blood pressure, what would happen if I intervene to give you blood pressure medication? Well, it's given by this expression here. I've got my features of A, I've got my features of V, and now I've got my conditional mean of my features of x given V, which is much easier than trying to sample from x given V, and I have now my answer. Let's now go to the demographic setting. Okay, so sorry, to the case of the youth employment program. So in the youth employment program, what we're going to do is we're going to condition on age. We're going to say of the individuals of a certain age, what would happen if we made them take a certain number of hours of in this program. Okay, so on the x-axis here, we have the number of hours that we're intervening on. So we're saying, look, we've observed this system, and now we're going to intervene. We're going to make people of a certain age take some number of hours of training. And on the y-axis here, this is the age that we're conditioning on. So we're saying, of people who are 16 years old, what would happen if we gave them this many hours training? People who are 20 years old, what would happen? So what we're kind of doing, we're slicing at different ages. We're slicing across this graph, and we're saying at this age, what would happen if the people took some number of hours of training? What you can see here is that, at 16, you can increase employment from 28% to 36%. If you slice at 22, increase employment from 40 to 56%. So if you're making policy, you're deciding on how to allocate funds for this program, then you might decide to fund certain ages over others because you're getting better results for certain age groups and for others as a function of the amount that you spend. So this is a very useful tool if you're a policymaker and you're trying to design a program of this kind. One final thing you can do is you can have, rather than a single treatment, you can have a sequence of treatments. So a famous case is in the treatment of HIV, where you're actually basically like applying a sequence of medications, and following each medication, you're seeing changes in the patient conditions. And following those changes to the patient conditions, you're applying a second piece of medication, and then you're going to get some health outcome for the individuals. So this, of course, looks a little bit more complicated because rather than just doing a single treatment, you're doing a sequence of treatments, each of which depends on the previous one in the sequence. But nonetheless, the mathematics that I've described apply equally well to this setting. So this is called dynamic treatment effect setting. And we're able to basically determine the effect of interventions in this setting from having observed logged data of this setting. So I just want to pause briefly here in case there is any questions. Okay, not yet. All right. So now I'm going to make my problem a little bit harder. Okay, so I'm going to say, what if there are hidden confounders? Yes?
Okay, there's a question, Arthur, and
Yep.
I can read the question for you if it helps. So,
Sure. I was going to try and find my chat. Here it is. Yes, the lasso structure in the last layer. Oh, okay. Sure. So in respect of the lasso, okay, That's actually a very good question, right? What I've got here is a linear final layer. Um, the regularization that I'm applying, though, is a sum of the squared norms, not a lasso. What that means is that I'm not enforcing sparsity here. I'm stopping my f's from blowing up, but I'm not having a situation where I'm only allowing a sparse subset of the f's. In the setting that I'm considering, this is, I think, the correct approach. Um, but yeah, like I would say, you're absolutely right. Like, if you start enforcing sparsity and that's a bad assumption to make, then you're going to end up in trouble. In the studies that we did, we never enforced sparsity. In the studies that we did require that these Fs didn't grow too large. So this is what this does here. But we did not, let's say that most of them have to be zero or anything like that. So I hope, John, that answers your question. Okay, and I see another question. Um, yeah, so I would say nonlinear complicated systems, this is absolutely the kinds of settings that we should be considering for this. In particular, what we've done is to featureize the context variables, so the variables that we're using to, let's say, predict the effect of some intervention. These variables can be very high dimensional. They can be images, they can be like, sequences of images, they can be anything on which you can define a neural net to discover relevant features. And the procedure that I describe is going to basically like learn these relevant features in order to best predict the effect of particular interventions. Now, these interventions can also be very complicated. So, when we're sort of talking about actions that we can take, these actions in this graph here need not be just binary valued. These actions can be sort of very high dimensional. I hesitate to sort of say anything specific to ecology because I don't know much about ecology. But in the context of Google, let's say, my interventions could be outputs of an LLM. So these could be like sentences or phrases. They could be images. In medicine, this could be like a treatment regime, like a radiotherapy regime. So these A's can be very complicated, very high dimensional. And the interactions between A and Y and X and V, these can all be nonlinear, very complicated nonlinear interactions, and that's totally fine. I hope I've been able to answer those two questions. Is that helpful? Okay, I'm going to keep the chat alongside my slides so I can see if any other questions appear. Okay. So I want to basically like address perhaps briefly the case of hidden confounding. So let's now move to a slightly different regime. Um, I am an economist, let's say, and I'm studying the effect of ticket price on the number of seats that an airline can sell. So I'm basically studying the effect of ticket price on demand for seats for an airline. And what I want to study is the effect of intervening on ticket price on the number of seats that I sell. Now, let's say that I'm observing my data. On the x-axis, I see the price at which I've set my tickets. On the y-axis, I've got the number of seats that I've sold. And this is what I observe. Now, let's say that I haven't listened to this talk. What I might do is then to do a linear regression and say, I'm going to conclude now that if I increase my ticket prices, I'm going to sell more seats. So plainly, I've done something wrong. What have I done wrong? Well, what I've neglected is that both the price and the number of seats sold are functions of an underlying level of demand. So here I've just assumed that demand is given by this variable x, and it can take one of three values. Either demand is low in winter, it's high in summer, and it's very high during vacation. Okay, so demand with high probability takes one of three values. And then, depending on demand, well, the airline has an algorithm, right? And if demand is high, they're going to increase their ticket prices. If demand is low, they're going to reduce their ticket prices. So that's basically governed by this equation here, where the price is going to increase when demand increases. It's going to decrease when demand decreases. Now there's an additional z variable here. I haven't told you what that is yet, but keep that in the back of your mind because that's going to come back. Okay? But price goes up when demand goes up. Airline algorithms, that's how they work. And then we've got the number of seats sold, and this is governed by this equation here. So what this is going to do is to say, well, look, number of seats sold is obviously going to drop when the price goes up, but it's also going to be governed by demand. And so you're going to sell more seats regardless of price when demand is high. You're going to sell fewer seats regardless of price when demand is low. And so that's the sort of the two factors that are working together to influence the number of seats that you sell. All right. And you can kind of see the pattern, right? You can see in this plot here, here's the low demand regime, here's the medium demand regime, here's the high demand regime. Now, we've already learned how to deal with this confounder, right? We get the average treatment effect. So we say on average, over all of the levels of demand, what would happen if we adjusted our price? And so here I'm averaging over all the levels of demand, and then I get basically like a negative effect of price as I would expect. So on average, over those levels of demand, as I increase my price, I'm going to sell fewer tickets, all else being equal. Great. That's all well and good, but sad for me, I don't get to see this. Okay, so is there anything I can do, right? I'm in trouble. Now, there is something I could do. I could ask the airline to do a randomized control trial. I can go to the airline executive and say, look, I want you to set your prices at random. And then I'm going to tell you the effect of price on demand. And then the airline executive is going to laugh at you and send you on your way. So there must be another way to do this, right? Now, the way that we can do this is by returning to this equation and now looking at this z variable. So this z variable is actually the price of gasoline. Price of gasoline is going to influence the price at which the airline sells their tickets. So when price of gasoline is high, I'm going to be forced to raise my prices. When price of gasoline is low, we're in a competitive environment, I'm going to drop my prices. And that's what we're observing here. So what we're now going to do is basically to condition both sides of this equation on the price of gasoline. So I'm going to map from A, ticket price given Z, to Y, number of seats sold given Z, and I've got this function here, which is my X given Z. But in the example, this X given Z is actually 0. It goes away. And so what I'm left with when I condition on the price of gasoline, I see that I get the downward sloping trend that I was after, right? So this is using the price of gasoline as what we call an instrument. We are able to recover the effect of price on ticket sales, even though we don't get to observe this X. And why is that? It's because we've been able to average away the effect of that X using this, the fact that the conditional mean of X given Z is 0. So to conceptualize this is like a natural experiment. It's like, life is forcing you to make an experiment. So I said, if I told the airline executive you have to set your prices at random, they'd laugh at you. But then this price of gasoline is effectively forcing the hands of the airline, right? It's forcing the airlines to increase or decrease their prices in a way that, in our example, is independent of the underlying demand for travel. And so that's sort of nature's experiment, and it's a way of basically like getting the causal effect. So instrumental verbal regression was the subject of the Nobel Prize in Economics in 2021. A lot of, I think, the art of doing these studies is in identifying a good instrument. So I've sort of said, like in this toy example here, it's the price of gasoline. But in practice, it is a real science to get good instruments for problems, which have this sort of nice effect of making nature's randomized control trial. And so these individuals were able to do that very effectively. And yeah. Okay. So this is in the abstract what instrumental variable regression is doing. But we're interested in the case where like A is very complicated, high dimensional, Z is very complicated, high dimensional, all these effects are nonlinear, very complicated, and so on. So we're now going to address how to solve this with neural net features, in the event that everything's very high dimensional, everything's very complicated. Okay, what assumptions have we needed to make? We have needed to make the assumption that this hidden thing given Z is 0, right? The mean of the hidden thing given Z is 0. And we've had to make the assumption that this hidden thing has an additive effect on Y. What does that mean? That means that my underlying demand factor for travel can sort of shift up or down the number of seats that I've sold, but it can't do anything more complicated than that. So we're making actually a strong assumption on the way that the demand influences the number of seats that I sell. Okay, this is a strong assumption, but we need that in combination with this to get rid of this term. Okay, one other rather obvious thing, the Z has to influence A, right? Because if it didn't influence A, I wouldn't be doing a randomized controlled trial, would I? Right? I have, if Z had no effect on A, I wouldn't be adjusting A at random independent of X. This is a very difficult expression to parse, but what it means is that I'm assuming that there's no underlying hidden factor U here, which I don't get to see, which is influencing both Z and Y. I'm ruling that out. Okay? The only way that Z influences Y is via A. Okay, so these are the assumptions that we're making. If we make these assumptions, well, we'd love to be able to get the average causal effect, but we're not able to because we don't get to see X. But instead, we can recover the expression for the average causal effect by conditioning on Z. Now, I'm making the modeling assumption here that Y is a neural net function of A, right? So that's another way of saying that is that, my dependence of Y and A can be very complicated. A can be very high dimensional. This is all fine. Okay. So we can solve this with kernels. We can solve this with neural nets. I'm going to focus on the neural net solution. How do we solve it? Well, remember that we're trying to find the regression from the A given Z to Y. The only algorithm in this talk is ridge regression, so we're doing it with ridge regression. How do we get the conditional feature mean of A given Z? I've told you how to do that already, right? You just do it by learning a matrix F, exactly as we did for the conditional average treatment effect. We learn this matrix F using ridge regression because there's only one algorithm in this talk and it's ridge regression. So we use ridge regression to learn this F. That gives us our conditional feature mean. We then use that to predict our Y. Now we also need to learn the remaining neural net features. We learned the theta neural net features from this loss by backprop. We learned the zeta features from this loss by backprop. And what we're going to do is to alternate because, obviously the best features here are going to depend on theta. So we're going to basically alternate the two of these. We're going to update our theta, we're going to update our zeta, and we're going to go back and forth until we get some solution. So this is how we do instrumental variable regression. I think, briefly, where we apply this is in reinforcement learning. So this is basically like action in pursuit of reward. What we're trying to do here is to basically estimate discounted future reward starting from some point and taking some action. So to give an example, let's say that we have a car which is trying to get up a hill. Here's a car, here's a hill. And the car is going to sort of rock back and forth until it reaches the goal. And the closer it gets to the goal, the more reward it gets. Okay? So then the car is going to basically, decide on, depending on where it is on the hill, it's going to decide on the action it wants to take. And that action is going to be a policy. So this pi is going to say, take this action when I find myself at this point on the hill. Okay? And then I'm going to say, look, for a given tactic for getting up this hill, I'm going to get a reward. And this reward is going to be given by this. And so, obviously, what am I interested in? I'm interested in, how good of a reward am I going to get by different policies? So for the car going up the hill, if it strains and tries to get up the hill in one go, it's not going to make it. It gets stuck. But if it rocks back and forward, then eventually it will make it all the way up. And so that, the rocking back and forward is a more successful policy than just trying to drive towards the flag and failing. So without going into detail, it turns out that this problem of learning the reward of acting with a policy can be understood as an instrumental variable-like problem. And for a bunch of reinforcement learning settings, we're able to get very good results. So here is the mountain car, so the car going up a mountain. What we're doing here is adding some sort of jitter to the car's motion, as a function of the inputs. And we're seeing that our method is performing well, so lower is better, and in fact performing comparably to a sort of specialized method that is applied for this setting. So that's I think very encouraging, and this is I think a scenario where this instrumental variable approach is very helpful. Great. So I think at this point, I've introduced IV. I will skip the proxy methods, but I want to just perhaps conclude. So, just to summarize, what we've done is to look at neural net and kernel solutions for average causal effects, conditional average causal effects, dynamic treatment effects. Even in the event that we don't see the relevant covariates, so even when we don't see those, there's still something we can do. And in particular, the settings that we're considering allow us to use treatments, covariates, etc., which are very complicated, very high dimensional, because we are able to use either kernel or neural net features to basically treat these complicated settings. As I emphasize here, code is available for all methods. And as I've expressed here, like the only method that I use in this whole talk is ridge regression. So ridge regression is all you need to solve all of these causal problems. So this work was supported by Gatsby Charitable Foundation and Google DeepMind. And I'm happy now to take any further questions.
Thank you very much, Arthur. And there's already one. I will read them. And the echo.
Yes.
Yeah.
Weak and strong instruments. Excellent question. We have actually a paper which we have just had accepted to NeurIPS, which is addressing exactly that problem. At a high level, what it's sort of saying is that I've got, let me go back to my IV. This is a question I really like because we just addressed it recently. Because absolutely, like weak instruments in the linear case are kind of easy to define, but in the neural case are hard to define. Okay. So what is a weak instrument in a non-parametric setting? What I've got here, I'm trying to learn a function from A to Y, right? A function from A to Y. But I'm learning that from the conditional mean of A given Z. Okay? So basically, what I need is my function from A to Y to be in the eigenspectrum of the conditional mean of A given Z. So I've got my conditional probability of A given Z. That gives me basically a dictionary of functions on A. So the eigenspectrum of that A. Now, if my function from A to Y is a function of the high order eigenvectors of the A to Z, then I have in a non-parametric set a strong instrument. If the A to Y is right in the tails of the A to Z, right? So it's basically looking at extremely low, eigenvectors with very, very small eigenvalues, then that's almost impossible to learn. So that is weak instrument in the non-parametric setting. So it's sort of saying like, what I can predict of A from Z has to also be what I need to use to predict Y from A. That's a way to express it. Yeah. So excellent question. If you look at the NeurIPS paper, I think Vladimir Kostik is an author, Dmitry Meunier is an author. It's a paper we're presenting at NeurIPS. It's on my webpage. This explained in much more detail this sort of notion of weak and strong instruments for non-parametric IV. So I encourage you to take a look.
Okay. Thank you. And then we have one last question. How do you validate causal models which you have learned from observed data?
Right. So this is a very good question, right? Because I've made like a bunch of assumptions, right? I've sort of assumed that I've got this X and it's hidden here and it's having an additive effect on Y. When I was doing conditional error treatment effect, I was assuming that there was no additional hidden confounding. Now, there is sort of bad news here, which is that the only way to validate, if you've made a causal model from observed data, the only way to validate it is to actually use that model to intervene. So to say, look, I believe that when I give this treatment to people with high blood pressure, that they are going to be cured. So now I'm going to run a trial and I'm actually going to act according to what I believe to be true. And then I'm going to see if the reality reflects my model. Same with IV, right? I've done IV. I've basically assumed that X is independent of Z. I've assumed that X has an additive effect on Y. Now, the only way really to verify this is to go out in the world and say, look, I'm going to increase my ticket prices and I'll see if I sell fewer seats. So that is, on one hand, a little bit sad. What people have done in practice, though, is they've said, look, what I can do is I can just regress from A to Y. I can just assume that there is no effect. And then I can compare what I get from regressing from A to Y against the instrumental case, right, where I basically condition A on Z and regress from that to Y. If I get different answers, then that indicates to me that something's going on. So that there is some hidden confounding and that the instrument has had some effect in removing it. Does it have a complete effect? Like, has it removed this confounding completely? Well, we don't really know. We have no way of knowing. But at least we know it's doing something. So that's a slightly discouraging but honest answer to that question. Yeah.
Okay, thank you very much, Arthur, again. And it's now 6 p.m. So now we have finished today's session, and yeah, looking forward to more exchange in one of the upcoming events. And yeah, thanks very much.
Okay. Well, thank you. And yeah, I enjoyed the talk very much. Okay.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.